In this section, we are going to look at an application of implicit differentiation. And the problem that we're trying to solve is called the related rate problem. And whenever we see related rate, we are talking about usually is d over dt. So something is changing with respect to the time. So let's take a look at example 1. Water is flowing into a vertical cylindrical tank of diameter 28 meter at a rate of 11 cubic meter per minute. Find the rate at which the water depth is rising. So we need to understand, okay, what is given to us, and it's always a good idea and good strategy to write down what is known. So we know that it's a cylindrical tank. You can draw a picture. So this is the object that we are referring to. We know the diameter is 28 meter. And we usually want to know the radius instead of the diameter. So the radius in this case is 14 meter. It's half of the diameter. We know the rates. Okay, so water changing in a rate of 11 cubic meter per minute, and we need to pay attention to the unit because it's telling us the rate, like what is changing. Because it's cubic meter, we're talking about the dV, the volume is changing with respect to times. So anytime we're talking about rate, it's always d, okay, d something over dt. And in this case, we're talking about the volume. And it's changing at 11 cubic meter per minute. And what we want to find, okay, it's always a good idea to write that down too, so you know what your goal is. We want to find the rate at which the water depth is rising. So depth, we usually are talking about, okay, so how much water is here, right? So here we're talking about referring to the height, okay? So in a cylindrical, usually the parameter is the height, okay, and the radius, and then the volume. So we need to find a rate at which the height is changing. So dH over dt, we don't know what it is. So this is a problem. And because we're relating the volume, the height, and the radius, we want to call for the volume formula. So for any object, right, a cylindrical object is usually the area of the base times the height, and the base is a circle, so it's pi r square h. So that is the volume. Then we need to know, okay, what quantity is changing and what quantity is not. The volume is changed as water flow in. The radius is fixed because it's a tank. It's not going to change its radius. But the height is changing also because water is rising. So because we know the R is not changing, things that don't change when you talk about the rate at which it changes is 0, okay, because it's not changing. So we can just plug in R as 14. So our V will equals pi times 14 square times h. So in this case, when we want to find the dH over dt, all we need to do is take the derivative with respect to time on both sides. So take the derivative with respect to time. For v, it's just dV over dt. It equals pi times 14 square is a constant quantity, okay? So constant, we usually just copy it. So 14 square pi times, now the height is changing, so it's dH over dt. then in this case, we can solve for dx over dt because we do know dv over dt is 11. So the equation right now, we have 11 equals 14 square pi times dx over dt. So how to solve for dx over dt? We divide both sides by 14 square pi. So 11 divided by 14 square times pi equals dx over dt. So this is the exact answer for this problem. And then if you need to enter a decimal solution, you just use a calculator to do the calculation and then run it to however many decimal the question is requiring to.